Welcome to today's deep dive.
When bubble sort approaches a data set, let's say a really long array of unsorted items, it doesn't zoom out to evaluate the whole picture.
It can't see the forest for the trees.
Exactly. It starts at the very beginning of the array, and it only looks at two immediate adjacent elements at any given time. So it just evaluates item 1 and item 2.
Imagine you're standing in front of a shelf and you're tasked with organizing this messy row of books by height.
Shortest on the left, tallest on the right.
Right. But you're wearing these heavily restricted blinders. You can literally only see two books at once, just the two directly in front of your face.
So you examine book 1 and book 2.
Yeah.
And if they're out of order, meaning, the book on the left is taller than the one on the right,
Yeah.
you exchange them. You physically swap their positions on the shelf.
Okay.
And once you make that decision and execute that potential swap, you take exactly one step to the right.
So you literally just shift your blinders.
Right.
Now you're looking at book 2 and book 3. You compare them, you swap if necessary, and then you just take another step to the right. Then you check 3 and 4.
And this step-by-step march continues strictly from the beginning of the array all the way to the very end. And by relentlessly forcing the larger item to the right at every single step, you guarantee a very specific mathematical outcome for that first pass.
Which is that the absolute largest, heaviest encyclopedia on that entire shelf is going to be continuously dragged to the right, swap after swap, right?
Exactly. Gets dragged all the way until it hits its final correct position at the far end of the array.
Bubbling up to their proper position?
Which is exactly where the algorithm gets its name. Every single complete pass through the data guarantees that the next largest unsorted element bubbles up to its final resting place.
And then we have to walk all the way back.
Yeah, once you hit the end of the shelves, you walk all the way back to the start line, and you repeat the entire restricted process over again.
That's right.
You do this pass after pass, just looping through the data until the entire array is sequentially perfect.
Picturing this, just the constant shuffling, sliding heavy books around, walking all the way down the line, trudging back to the beginning and doing it over and over. It just feels like an exhausting amount of physical movement.
It is a lot of movement.
I always assume that when a computer executes a process like this, the constant physical shifting of data back and forth in memory was the most computationally expensive part of the job. Like, wait, isn't the constant shuffling the part that bogs it down?
Well, what's fascinating here is that the physical shifting of the data, the actual swapping of the items, isn't the true bottleneck at all.
Wait, really?
Yeah, the massive hidden cost of this algorithm is the comparison itself.
Huh.
We have to transition our thinking from the spatial movement of data to the actual processing toll of answering that fundamental yes or no question. Is item A greater than item B?
Oh, I see. So the cost depends entirely on the nature of the data being sorted.
Precisely.
Because we know that if the system is sorting, like simple integers, evaluating whether 5 is greater than 3 is mathematically expressed as operating in constant time, or O of 1.
Right, because simple numbers are the native language of the processor. Executing a binary check on two integers happens at the hardware level in, like, a fraction of a clock cycle.
It's nothing.
It barely registers as effort.
But the dynamic changes completely when you ask the algorithm to sort complex items. Imagine we aren't sorting integers, but we're sorting massive 50-page legal contracts.
Oh, wow.
And we need them ordered alphabetically by their actual text contents.
Okay, yeah, that changes the scale of the question entirely. It's obviously no longer a simple O of 1 integer check, which is exactly why the comparison, not the physical swap, is what grinds the system to a halt.
Loops, even if the list was already completely sorted on the first try.
Which leads us naturally to the algorithm's built-in defense mechanism. It actually possesses a really vital degree of self-awareness. It features early stopping.
Okay, so it tracks its own progress.
Yes, during every pass.
So it might have tunnel vision, but it isn't, entirely oblivious to its environment.
Exactly. If bubble sort completes a full pass through the entire array, meaning it compares every adjacent pair from start to finish, and it executes absolutely zero exchanges.
Well, yeah, if nothing was swapped, that means every adjacent element is already perfectly sequenced.
It realizes the job is done. So instead of rigidly executing all the remaining passes it mathematically could perform, it just terminates the process immediately. Translating that to the algorithm pseudocode, we start by setting our search area. We initialize a variable called bound to n-1, where n is the total number of items.
Right.
And that sets up a loop that runs while bound is greater than 0.
Okay, so we have this main loop running. What happens inside it?
Well, at the very start of each pass, it sets a Boolean variable called swap to false, and it also sets a tracker called lastExchg to 0.
Oh, got it. So it resets those before doing any actual comparing.
Yes.
Yeah.
Then we drop it to a for-j loop. This moves through the array, strictly comparing those adjacent elements we talked about, which the code calls a of j and a of j plus 1.
And if a of j is greater than a of j plus 1, the algorithm executes the swap logic.
Right. Because the largest element is constantly pushed right during these micro comparisons, it essentially bubbles up to its correct final position at the end of the array in just one full pass.
And the algorithm is performing that expensive check on every single adjacent pair over and over because of that tunnel vision you mentioned.
Exactly. So it needs a way to avoid unnecessary checks if the list is already mostly sorted.
Which goes back to those variables we set earlier, right? The swapped and lastExchg variable.
You nailed it. Every time a swap actually occurs, swapped becomes true, and lastExchg records the exact position j where that swap happened.
So if an entire pass finishes and swapped remains false, the algorithm knows the list is perfectly sorted and just shuts down.
Right. Early stopping. It also optimizes the next pass. Instead of checking the whole list again, it shrinks the search area by setting bound to lastExchg.
Oh, wow. So it completely stops checking the end of the list that is already sorted.
Yep. This smart stopping gives a best case time complexity of O of n. If the list is already in order, it just walks through it once and stops. And because of this self-awareness, the algorithm's efficiency fluctuates entirely based on the initial state of the data. If you hand bubble sort an array that is already perfectly sorted, it only has to make one single pass to verify it. That gives it a best-case time complexity of O of n.
Meaning the time it takes just scales linearly with the number of items just to check them that one initial time.
Exactly.
Hmm.
Even though its average and worst-case time complexity, which is when the data is randomized or, completely in reverse order, is O of n squared.
Which is significantly slower.
Much slower, due to the compounded comparison costs of all those repeated passes.